Okay, so I'm going to keep on going over solving differential equations. The other thing is, okay, I have two sets of books, a book of that, grade books I have here, books I have at home, and I try to keep them updated. I don't know if my grades for daily homework 7 are in my book at grade book at home or here. So did I handed back daily homework 7, did I not?
For me, no. I mean,
Because I cannot find it. I mean, yours is there. And you handed it yesterday. Did I not?
I don't think I got it back, but also I remember turning it in late. So
daily homework 7, is that the new daily homework that you
No, it's doing the.
Oh no, I handed it out. So like, I just
that's just the one with the spherical lens.
Okay, if you have it, can I keep it? Because I want to make certain that I actually have it recorded. Okay, so I did hand it back. So you do have it if you have it.
But I already gave it to you when I gave you homework 7, right?
If you hand it back to me earlier, then I hand it back to you. So check for yourself. This is great.
Okay.
I probably have it recorded at my one at home. I don't know, but I want to make certain I did not forget it. Because actually, when I was going to grade yours, I can't remember how much it was out of. But I pulled up the grade book and there's nothing there. Okay, that's not good. Okay, so with that said, suppose I have a differential equation like this. Oh yeah, so if you have it, it's you can just hand it that. Okay, so how do we go? So we go about solving that?
You check if it's linear.
Is it linear?
Yes.
Okay. Is it homogeneous?
Yeah, it is.
Second order. What do we know about the coefficients in front?
They're constants.
They be constants. Here we go.
You can do e to the px.
We assume an e to the px here. So we assume the y equals e to the px. Put this in here. This gives 4p squared e to the px minus 3 e to the px. E to the px's go out. This gives me 4p squared equals 3. So p is plus or minus the square root 3/4. So, what are the solutions? Y1 is one of the roots. So y1 is going to be e to the square root of 3 over 2x. Yep. Y2 is e to the minus square root of 3, 2 over x. So the most general solution is
the linear combination
is a linear combination. So your most general solution is C1 e to the square root of 3 yx plus C2 e to the minus square root of 3y. That all makes sense. So we applied this into our spring. So we had our little wall, we have our spring, here's K, this is M. We put it in the official daily homework. Remove this here. And what did this do for us? So the forces on the mass are
Minus kx.
minus kx. Looks long. And the net force in the x direction equals nix. So from that picture, the only force in the x direction is spring. And how do we write kx? Second counter over. This time. How do we solve this? So the coefficients are constant, so we assume x equals e to the pt. So this gives us what? This gives us minus k e to the pt plus p squared m e to the pt. E to the pt, well, this gives me p equals the square root of minus k over m, which we write better as, okay, it's going to be plus or minus I times the square root. And we call the square root of k over m. That's omega naught, the natural frequency of oscillation. We define, for m, and this is called the natural oscillation. Make sense? Questions? Now, one other thing about that, so to get more in the oscillation program. So that means we have two solutions here. We have x1 equals e to the plus I omega naught t, and x2 equals e to the minus I omega naught t. So the most general solution is, so I can write it as or, did we do that one yesterday?
Sine and cosine.
Yes. Or, then I'll get something to the constants. Or,
You treat C3 and C4 as sine by cosine of phi.
with a constant phi,
Divide them into, would it be sine omega t plus phi?
plus or minus phi, depending on how you set it up. So I can write this as mg is some new constant, I'll call it, we call it d. Sine, it could just as well be a cosine, depending on how you set it up. Omega naught t plus or minus, depending on how you set it up. Phi. You're all cool. Does that make sense? Okay. I'm going to take this version here just for the sake of argument. So let's assume x most general is, I'm just going to take the sine term. I graph this. Okay. What do we call this time here, right here? That's the time for one complete oscillation that you do. This is the time. Capital T, so this is capital T. Okay. So I put this in here. I can see that equals 0. So what does it mean about omega naught t? This argument is 0, that's 2. Omega naught t is 0, that's going to correspond to this. That has to be 2 pi, right? This is basically, this is omega of 0. This point here is, this is omega times 0, 0. This is omega times the p value here is pi. And right here is omega times p value. Okay. So the omega naught times t T, your time for oscillation is 2 pi over omega naught, or 2 pi square root of m over k. Right? And that's the hallmark of simple harmonic motion. What does this not depend upon? Time of oscillation? That depends on the k. Suppose I have a spring. I pull it out this far and I let it oscillate. And I pull it out this far and let it oscillate. Which one will have the different? Which one will have the greater oscillation? Is there an amplitude in this expression? There is no amplitude. This is independent of the amplitude. On the board. That's getting close. This right here, this is independent. And that will always be the case with simple harmonic. It will always be infinite. What was the argument I gave you? We're going to do a race, okay? So we're going to line everyone up. I'm going to have a starter's pistol. I'm going to pull the trigger. When you hear the gunshot go off, everyone runs. Okay? Then I'm going to pull the trigger again. You hear the second gunshot, everyone stops and comes back. Who wins? We're all winners, okay? So everyone, it's going to be a tie. Now, how come? Some people are going to be really, really fast. They're going to be way out in front. Some people can barely move like me, and I'm going to take like 4 steps and almost die. Okay? So what's going to happen? Gun goes off again. I don't have very far to walk. I mean, okay, I don't have very far to run, but I'm slow. Okay? Some people are going to be really, really fast. You're way over there. You have really, really far to run, but you're fast. And those two affects the distance and the speed actually. Okay. That makes sense? Now, we want to think with this a little bit. We now want to have a driving term on that. So what happens? So in our problem, the incident wave is oscillating, is driving the electrons oscillation. So remember, here's our nucleus. Here's this here. This is our nucleus. This will be positive. Here's a negative. We're going to have this electric field like this. The electric field's going this way. And so what happens here, we now have a driving term. So when we have this here, we have our, so we now have a driving term. So I'm going to make a mechanical picture of this. So this is analogous to that. I have a wheel here. This wheel is going to spin at some omega. Okay. And I have an arm connecting up like that. So when this goes like this, that's going to pull this back and forth like this. Okay. So now when I do this, what do? I have my minus kx here. Now I have my driving charge. This is my driving charge. And this is going to be some amplitude F naught, sine or cosine, omega t. Now I'm gonna do my net force in the x direction. And minus kx plus f naught. Okay, sine equals m. Second derivative of x is 52. Does that make sense? Hey, what kind of differential equation is this? Now a non-homogeneous differential equation. This is my non-homogeneous term. Question is, how do you solve linear non-homogeneous differential equations with constant coefficients? So, how do you solve linear non-homogeneous differential equations? With constant. We're gonna have something like this. AN, BNY, dx here. And that's 1. Equals now f of x. Does that show up? Yes, it does. We're gonna make we're gonna make some assumption. We will assume. F of x is, I'll put it in quotes, simple. That's gonna be my question to you. What does it mean to be simple? Let's see, I see two experts.
Is that a complex function?
Well, you're sure. Okay.
It's a linear function.
So, what does it mean to be simple? Constant. Sine or cosine. Polynomial. Exponential or product. Simple means the following. By simple, we mean f of x is constant, polynomial, sine or cosine, exponential, products of these.
Wait, so it's not all of them? Oh, no. You were saying that, and I was confused because I thought it was all of them. It's one out of those?
Yes.
Okay.
So I'm going to show you the technique to do this. In other words, you have to really just kind of do a whole bunch of examples of this to get used to it. So let's take a case. So let's take an example. So if I have this. Let's see. This is my. So what do we do? This we're going to do this following. So we're going to use a method called we will use the method method called undetermined coefficient. So what do? We look at f of x and all of its derivatives and look for the unique pieces. So we look at f of x and all of its unique functions from differentiation that occur during differentiation. We then assume a solution a solution which is a linear combination of these unique pieces. These unique terms and determine their coefficients. Okay, so we're going to do a whole bunch of examples. Okay, so here's f of x. This is x squared. Let's take the first derivative of this. Okay, what is the first derivative of x squared? 2x. So we could care less about the 2. We're only looking at the functional piece, which is x. Is x unique from x squared? Yes. Okay, now we take another derivative, which is 2. I could care less of the fact that it's 2, but it's a constant. Okay, so what are the unique pieces? Unique pieces are this is unique. This is unique. And then I'll circle this thing, the constant is unique. So we take a linear combination of these pieces. So I'm going to say the non-homogeneous solution is going to be some amount of this. I'll put an A in front of it. I have no clue what A is. A is a constant. Okay. Plus, now I have an X. I need some amount of that. And it's a D of that. And then some amount of this. That's a constant. So I'm going to say C. So that's actually going to be my form that I'm going to get. That makes sense. Now, let's go through and do it, and then I'm going to do more examples of figuring out these. So now we need to determine A, B, and C. And how do we do that? And you're done. Take the curl, set it to 0. Or the diversion. We're solved. Okay? It's diabolically simplistic. Okay? A, B, and C are 0.
Guess. Trying to get.
Okay. We're going to take that and substitute it into here. Okay? So we do this. By substituting Y and H into the region right there. So let's do that. Okay, so first derivative is 2 ax. Second derivative is 2. So now we put them in here. So what do we get? This guy is 2a minus 4. My y is over here. And this equals x. So what does that give me? This gives me minus 4 ax squared minus 4 bx. Then plus 2a minus 4c. Okay. So now we compare sides. So here's an x squared. Here's an x squared. So minus 4a must be 4. I mean, must be the 1. So if I this is a 1 here. So this gives us minus 4a equals 1, or a equals minus 4. We're done.
Oh no, we're not.
Correct. Okay, now what's the coefficient in front of x on this side?
0.
It's 0. Now if I look here, this term here, that's within. Okay. This is minus 4b, 0, 4b. Now what's the coefficient in front of the constant?
0.
I have a constant here. 0 here, so that means this whole thing here. Let's do that. So this gives me 2a minus 4c equals 0, or 2a equals 4c, or a equals 2c. So what that means is c is half of a. So we have a half. That's minus a quarter. That's an 8. So our non-homogeneous solution is minus 4, minus a quarter, x squared, minus a
Good question.
Yep.
How do we assume the function? Or we just say let's the function be this?
The f of x term?
Yes.
Oh, I just guessed that. This technique will not work if it's anything.
But like even if it's something simple, how do you guess? Because there's 1, 2, 3, 4, 5 things that are simple. How do you know?
Well, you'd have to depend on the differential equation. Okay. So for the driving term, for a spring, what's going to be the f of x? Let's try another one. Let's say we had this. Now, what would we then assume for our non-homogeneous solution? What do we do? We start off with this is our f of x. Take a derivative, which is
3x
what we're doing, right? I agree. So let's do it.
Okay. Oh, minus 3ax
3ax.
exponential of minus.
Where did the a come from?
I don't understand.
F.
Yeah, okay, but like
Derivative of f.
I said the answer.
Derivative goes here. I was writing down what you wrote. You said a.
I'm getting gaslight.
Okay. As it's been recorded, you said a. Okay.
Erase the 8.
I agree. But it should not be there.
Minus 3x exponential.
Okay, minus 3x
exponential
exponential.
on minus 3. That's oh my god.
You got
Okay.
more.
Does
Oh
Junior
my-
get to stay on the
oh.
island, or should we feed Junior to alligator?
Oh,
Okay.
plus
Thank you. Plus,
exponential of minus 3.
what are the unique pieces here? Is this piece unique? No, because this right here is the same. This is not unique. Okay, is this unique? This is unique. Now, I don't have to worry, when I take the second derivative, I don't have to worry about this piece as I've done it already. What happens if I take the derivative here? Same thing, so I can stop. I don't need any more derivatives. Now I look at the unique piece. This is unique. This is unique. So I'm going to assume that this is ax e to the minus x plus b e to the minus 2x. Does that make sense?
Ax to the minus x or minus
Oh, 3x. Thank you.
Oh.
That makes sense? Now what happened if I had this? Right, f of x is x squared. No. Oh, let's just say. Go over this one. What do you have to do? Derivatives. This is what? 2x sine of x.
plus
Plus 7.
plus x squared cosine x.
Okay, do we have unique pieces here?
Cosine x.
So what are the unique pieces?
X sine.
Yeah, this is unique. This is unique. There we go again. So let's do the second group.
Well,
Ooh. 2 sine of x. 2x cosine. Plus 2x cosine of x. Agree? Now we just look for unique pieces. Is this unique?
yes.
Okay, is this unique?
Yes.
Is this unique? It's the same as this. So it's the same as this. Is this unique?
No.
Not unique. So I'm not gonna get anything new from that. When I take the next derivative, I'm not even gonna worry. Third derivative. This goes to. Okay, try again. What do you say?
Cosine x.
Plus?
No, there's another unique
What happens if I differentiate this guy?
cosine of x.
I get what? I get 2 cosine of x, same as this guy. Then what?
Minus
Minus
2
2
x
x
sine.
sine of x. And then it's going to be the same thing as this guy here. Okay, this is unique. This is unique. This is not. Does it go on infinitely? I keep on differentiating of the unique pieces, so keep on going on. And then no, it stops. So what would you have here then? We're going to have then for a solution. What we have. I'm going to say that this is going to be A x squared sine of x plus B x squared plus sine of x plus C sine of x. C. That's what you have for that.
You have more. That's it.
I think I have all. Don't I have all the pieces? Oh, I dropped my x terms. Okay, sorry about that. Up an x here, and E sine of x. Thank you. Okay. Ouch. That one's funny. And usually when you solve these coefficients, they end up being something like 37 over 100. You know, negative 29 over 2000. They end up being bad.
That's the kind of stuff you should learn with it.
Turns out it is. That's what I said.
Can we expect this to be on test two?
No, this will be test two.
Oh, yeah.
Questions? So with that said, let's go back and look at our spring being driven by the spinning wheel. So apply this. To our driven you're going to have what? So here's our little picture. I'll redraw it again. I'm so clear. They're getting faint. It is not. Do this. Get the equation we had before. We have this minus kx. That's our driving term that I'm just going to be sine. So I'm going to write this as and normally what you're going to do is divide through by the m and you're going to write it in more user-friendly form. Okay, what is this? The omega naught squared. This is our omega naught squared. Oh, this should be over. You do this, I get this equation. Okay, so you tell me how to proceed.
Function.
This is our non-homogeneous term.
So
So we keep on differentiating that, looking for new pieces, and we only end up with the cosine. So our x non-homogeneous. We'll have what form? A sine omega t plus b cosine. And we need two derivatives. So this gives me first one is my omega a cosine omega t minus omega b sine omega t. What's my second derivative? Yeah, so minus omega squared a sine omega t minus omega squared b. That makes sense. Questions on that? Now we can make it like a little bit more user friendly here. Does this look like something? if I pull out in a minus omega squared here, let's do this guy. Does that look like something? That's my x. I can write this as minus omega squared x non-homogeneous. So I'm going to take this and put them all into here. So if I take this, put up into here, and I think that's getting too faint. That's interesting. That barely shows. And that means oscillating. Intended it to. Okay. So this gives me what? This gives me minus omega squared x non-homogeneous. That's this one. I get this term here. It's omega naught squared x non-homogeneous equals f naught over m sine omega t. That's after you take the curl.
Oh my god.
The vector identity where the curl of everything is.
You missed the rule. Zero. Omega, right?
No, that's correct.
Oh, that's not omega. Oh, that's why it's not equal to zero.
So I can pull this guy out. I wrote this as omega naught squared minus omega squared. X non-homogeneous. That. Actually, in this case here, I can just solve for it. So my x non-homogeneous. It doesn't always work. Usually a lot more. Boom. What's unique about this? Okay, what's omega naught again? The natural frequency of oscillation of the string. What is omega?
Oscillation driving force.
Yeah, the rate at which that thing's spinning around. Okay. This right here is your amplitude. What do you notice about the amplitude? As omega gets closer and closer to omega naught, what happens? It gets larger and larger and larger. So as omega goes to omega naught, the amplitude increases. What happens when omega equals omega? Goes to infinity, right? Depends on whether it goes to plus infinity or minus infinity. What's going to happen is that if, let's say, omega goes to omega naught, we want the lower side up to there. Let's say, actually, let's draw this. I can graph the amplitude. I go, let's say here's. So if I'm far away from this, what happens? Let's say omega is really, really tiny. If this omega is really, really tiny, I just get this f naught over m omega naught. You get this right here, f naught m omega naught squared. As I start approaching, as omega starts approaching omega naught from this side here, what does that term do? Go like this. What happens if I'm on this side of it? This side of it. This is going from minus infinity here. It's going to go like that. It's going to start approaching back. That makes sense? Are you happy with that? Right. Once I go past this point here, this bottom becomes negative. Okay, this will be a negative infinity. And then as this one gets bigger and bigger and bigger, it's going to stay negative here. And then eventually what's going to happen here, actually it'll go to I should have a negative here instead. It's going to go to, actually no, that's just going to go to 0. I'll draw this to 0. Actually, that's great. That makes sense? Now, what's going to happen is that this is going to be the behavior when we have our little picture here. So here's our little wave. Here's our electric field. Here's our little atom here. This. What's going to happen? There's going to be a natural frequency for this. When this incident wave, which is omega, matches this natural frequency here, what's going to happen? We're going to have really, really big amplitudes here. So what's going to happen to the polarization then? It's going to be very large. So the susceptibility is very large. Okay. So what's going to happen? That's going to actually change the index of refraction. Does that make sense? The polarization is really intimately connected to that to your index of refraction. Not just that, we're going to see that chi is frequency. That actually depends on the frequency of the light. Okay. That makes sense. So we'll pick this. Okay, first of all, is this physical? No. This is not physical. Okay, usually how would I make this picture more physical? What did I omit in the mechanical picture? So we're going to put a friction term that'll solve the problem. What we'll also do, we'll get all this all listed up, and then apply it, and then I'm sure everybody got the quantum mechanics. Actually, we're in good shape with that. This makes sense? What would happen if there was like more than one? Oh, okay, I didn't give you the name for this. This is called resonance. The fact that you get really, really big amplitude when you're driving something at the natural frequency of that physics. It's the same thing as when you're swinging it as a kid, you pump. Okay, what are you doing? Well, you're matching your feet going back and forth with the natural driving frequency of this way. So when you're a kid, you get those really, really big arcs. Okay? When you're a kid, it's great. So enough, you can actually make the actual swing set start rocking. I don't know if you have to find that. Then you can't say stop that. For good reason. Okay, have a good day. I don't know how anyone survives a childhood.